Okay, so last two problems of the review. Again, we're given nothing. We have no picture to start with, no kind of sense of what it looks like, so we have to create this in our heads. I'm gonna repeat the advice from the last video. Just draw the picture. Like pretend you're standing way off to the side and you're seeing this happen in front of you. That will give you a picture of like a sense of what it looks like. Draw that, we'll find the triangle afterwards, okay? So here's what we have. So Miss Marcus and Miss Simmons have had it with students not turning on the cameras and are going on vacation to relax, but are leaving Mr. Hancock behind on the ground. Well, that's very sad, isn't it? After a few minutes, Miss Marcus and Miss Simmons, who I guess are in a plane at that point, right, have traveled 2,500 feet from the airport and are 6,300 feet in the air. I guess we should have specified they're taking a trip on a plane, right? At what angle of depression do they have to look to see the sad and abandoned Mr. Hancock? All right, let's draw the picture. So again, every single time we started with the ground, guess what I'm gonna start with? The ground. So that gives me a sense where everything is relative to each other. And so here we have the ground. So we have Ms. Marcus and Ms. Simmons, they're flying in a plane. Mr. Hancock's on the ground at an airport. And so let's draw Mr. Hancock. Okay, he's sad, but he's in an airport. And I assume that's what the airport's going to look like, something like that. Ms. Marcus and Ms. Simmons are in a plane. Okay, so the plane is 6,300 feet in the air and 2,500 feet from the airport. So it's kind of like away from Mr. Hancock. Okay, so here's like my best rendition of a plane. All right, got a tail in there. Probably another wing would be good. Okay, so they're in that plane and they're flying away. Why did they give the plane an eye? I don't know. It just happened. All right. So let's see. They are 6,300 feet in the air. So I know from the plane to the ground is 6,300 feet. Okay, and they're also 2,500 feet from the airport. And so 2,500 feet would be like this distance. Okay, and they look down at Mr. Hancock. Well, that means they're looking from the plane down to Mr. Hancock. Okay, so look at that, we have our triangle. Like I said, if we just draw the situation, the triangle usually evolves. There we go. We want to know at what angle of depression the teachers have to look back down to Mr. Hancock because he's sad and stuff. Well, the angle of depression, remember, is not going to be this angle right here. That's where most people are going to want to put the angle of depression. That's not the angle of depression. The angle of depression is if they were looking straight out and then they had to look down to see Mr. Hancock. This is the angle of depression. Okay, we're going to call that like our X because that's the question that we're really trying to find. So we're kind of in this spot where we don't actually have an angle of depression in our problem, or an angle defined, or let me rephrase. The angle of depression isn't even part of our triangle where we have all our numbers. And so if it's not actually part of the triangle we're trying to solve, how are we going to find that value of X? Well, we've talked through several examples of these, so we know that this is a solvable problem. I think the easiest way to solve it is if Miss Marcus and Miss Simmons have to look down to see Mr. Hancock has to look up to see them. And so this X also appears here as well. Now there are mathematical reasons for that, right? Alternate interior angles, for example. But logically, if somebody looks down a certain amount of degrees, they have to look up a certain amount of degrees for them to see each other, okay? Now, because the distances involved, we don't really have to think about like the heights. Like Mr. Hancock's height is going to be relatively the same no matter what. So I erase part of this. Okay. And so Mr. Hancock, even though he's presumably standing up, the distances involved are so far away that we don't actually consider his height. Okay, so it's going to be the same. But either way, I have an angle I can find. Even though it is the angle of elevation, it's not really the angle of depression. Okay. It's the same as angle of depression, and so if we find Mr. Hancock's angle of elevation to the plane, it's the same as the angle of depression back down to Mr. Hancock. I think I have a solvable triangle here. All right, so let's do some labeling. If I use X as my reference angle, We have 6,300, which is our opposite. Okay, and we also have this distance along the ground, 2,500, which is our adjacent. Okay, so that's going to dictate which function we're going to use. Okay, so referencing information, actual information, we have opposite and adjacent which to use. And so we have O over A. That equal sign, man, equals the O over A of a certain reference angle. In this case, it's going to be the angle x, or at least x degrees. Okay, O over A is our old friend tangent. And so if we use x degrees as our reference, and our actual triangle opposite side is going to be 6,300, and our adjacent side is going to be 2,500. So we have both side lengths, and so we have to get the x degrees, which means we got to kill tangent. So it's going to be an inverse problem, where we apply the inverse tangent, not just to one side, but to both sides. Okay, so on the left-hand side, we're applying it to the tangent value of x. Okay, on the right-hand side, we're applying it to the ratio 6,300 over 2,500. All right, so by rule, tangents cancel, leaving us with just x degrees. And so if we decimalize the tangent ratio, we can search for the angle. So 6,300 divided by 2,500 is 2.52. And so the angle of depression or elevation, because they have the same value, is 68.356 degrees. Okay, in other words, Ms. Marcus and Ms. Simmons have to look down at about 68 degrees to see Mr. Hancock, or reverse that, Mr. Hancock has to look up at 68 degrees to see the plane flying away because they took a vacation and they left him. All right, last problem. Excuse me. All right. Okay, Miss Simmons went ziplining on that vacation that she and Miss Marcus just took. So when she got home, she immediately wanted to run a zip line from the top of her house to the ground, probably for quick getaways, because you always need that. Zombies, you know. So she ties the rope off at the top of her house, 45 feet off the ground, and throws it to Miss Marcus on the ground, who walks away from the house until it is stretched very tightly. If the rope is 125 feet long, what angle of depression does Miss Simmons look down upon Miss Marcus? Wow, okay. So this is going to be kind of similar to the last question where we have like an angle of depression we have to find. But again, I'm just going to worry about drawing the picture. I'm sure we'll figure out the triangle as we go. All right, so here is the ground. So first of all, Miss Simmons is standing on top of her house. I'm just going to draw a simple house here. I know she probably has a roof, blah, 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 but let's just go with this for now. Okay, so she attaches a rope to her house, throws it to Miss Marcus, and then Miss Marcus walks away from the house until it is stretched tightly. Okay, so then Miss Marcus is not next to the house, she's going to be over here. Okay? All right, so the rope is going to go from the house to Miss Marcus, who's presumably holding it very tight. And she's a certain distance away from the house. Well, guys, I see that triangle forming right in front of me. Okay, so I have the triangle right here. Okay, not perfect, but we're just kind of sketching it out, right? In fact, we even have some values. We know that there's 125 feet of rope, so it's 125 feet this way. And it's 45 feet off the ground, so that means we have 45, which goes from here to here. All right, and so when the stretch tight, Ms. Simmons is looking down at Ms. Marcus, and we want to know the angle of depression. Well, we know, we just solved a couple of these. We know we have to start like straight out and go straight down to find the angle of depression. But it's the same as Ms. Marcus looking back at Ms. Simmons. And so we can also just say we want to find this angle right here. Okay? And so even though this is the angle of elevation, it is the same as the angle of depression. And so x degrees would actually be in both spots. Okay? That seems familiar enough to solve. And so if I use my x angle, the one at Ms. Marcus, as my reference angle, okay, labeling the side lengths, I have 45 is going to be opposite right up against the house. Okay, and then I have 125 as my hypotenuse, which serves as a strength. Okay, that seems familiar too. So opposite over hypotenuse, that's going to be my ratio. Opposite over hypotenuse for a certain angle is same as opposite over hypotenuse for the triangle I'm trying to solve. In this particular case, the angle is being called x degrees again. Okay, so over h, sine, cosine, tangent, that's going to be sine. It's going to be something. I don't know what word that is. Okay, so sine of a certain angle is going to be equal to a ratio in my actual triangle. So x degrees is a reference. In my actual triangle, the opposite side is going to be 45. And the hypotenuse side is going to be 125. Right? Well, again, we have a trapped angle, so we have to kill the sine function. So we'll bring in the inverse sine. Not just to one side, but of course to both sides. So on the left-hand side, we'll apply the inverse sine to sine itself. And on the right-hand side, we'll apply it to the ratio, 45 over 125. Okay, on the left-hand side, the signs will cancel. Okay, and so we just need to find the inverse sine of our ratio. So let's decimalize 45 divided by 125 first. And then find the inverse sine value, which means the angle of depression and the angle of elevation is going to be 21. It's not exactly 21. I jumped the gun there. Rounding to the nearest whole number is 21. But with decimals, it's going to be 21.100 degrees. Okay, and so the angle at which Ms. Marcus looks up and Ms. Simmons looks down is 21.1 degrees. All right, guys, that's your entire 22-page review, which I know seems like a lot, but you guys know by now, like, it's just a bunch of problems spread out. That's why there's so many pages, because I don't have to print this year, so, you know, I can make it however I want. So it's important that you finish all these problems. So if you're here with me listening to this, that means you're trying to get better and you're trying to do well in your tests, so I appreciate that. In fact, we all appreciate that. So thank you very much. That's the last part. And so remember, your test is going to be Wednesday, December 3rd. And so hopefully you're listening to this before Wednesday, December 3rd. But that's how she goes. So good luck on your test. Hope you guys get an A. Remember to ask your teachers questions, attend their office hours, whatever you need to do to get your questions answered about trigonometry. All right, thank you.